Quadratic inequalities. So these are a real booger because they're kind of hard to wrap your brain around when you're just doing them pen to paper with just like an algorithm. I really like to use a visual analysis to do most inequality graphing. We can look at that in a little bit when we go to Desmos to analyze why these work. So let's look at this question. X squared is greater than x. Solve for the x's that meet this requirement. So I'm going to shift my x over to the other side and say that this is a statement that can be graphed as x squared minus x, which means my roots would be x minus 1. I'm just going to pull that x out, times x is greater than 0. So if I were going to graph that function, I would use my roots, which are going to be at 0 and 1. And then it's a positive quadratic, so I don't really need to know much more than that. It'll look more like that. And I can see what this function would look like only in a brief sketch. I don't need any details. I just need to know where it's bigger than 0. So I'm going to figure out where it crosses the x-axis, which would be an output of 0. DP side note here, a lot of the time I see questions like this on those tests where they give you some function and they say express the following function or determine the output of, let me say that again, determine the input of x that meets this requirement. So where is f of x greater than 0? This is a great graphing calculator question because you can just plug this into your calculator, figure out what the roots are, and say it's bigger than 0 everywhere that the output is bigger than y equals 0. Okay, so when I'm looking at this graph right here, I can see that x actually equals 0 at 1 and x equals 0 at 0. So both of these output 0. So if I want to know when the output is greater than 0, it's when x is greater than 1 and when x is greater than 0. I'm saying that wrong again. Sorry guys. When x is greater than 1, so I had that right the first time, and then this is 0. So when x is less than, why do I keep saying 0? And I'm going to go back and highlight those in color because I just botched that whole thing. So x is greater than 1. That would be this section right here. And x is less than 0. That would be this section right here. All of the values of x less than 0 provides an output that's greater than 0. All of the values that are greater than 1 provide an output that is greater than 0. Here's another example. We're not going to go through the whole thing here. We're going to just skim over it so you can see how I would do this one. Bring our negative 4 over. This becomes negative 14, 0. I didn't pre-do this, so I'm going to check really quick. 3 times 14 is 42. Negative, so I'm looking for a pair of terms that add to give me negative 19x. So negative 21 and positive 2. So instead of using the box method here, I'm going to do this all on this side. I'm just going to provide you an additional strategy to factor that can make your life a little bit faster. So I'm going to look here at this side and see what the greatest common factor is. It's 3x, and when I pull that out, I get x minus 7. And then when I pull my greatest common factor out here, it's 2, and that also gives me x minus 7. So if I were thinking of this like a box, I could see that 3 times x minus 7 gives me these two terms, and 2 times x minus 7 gives me these two terms. So if I had something like 3x times a, we're going to let this whole thing be represented by an a, plus 2 times a. I could factor the a out. So I would have a times 3x plus 2. So I'm going to do that same kind of thing here. I'm going to factor out the common term, which is x minus 7 from both of those, just like I did with the a, and I would be left with 3x plus 2 greater than or 0. So same kind of thing. I don't really care for all the details. X actually equals 0 at 7, and x actually equals 0 at negative 2/3. So if I was going to do a sketch of this, it's positive, so I know it's going to open upwards. I'm just going to throw my points on there. They don't need to be really super accurate. There's negative 2/3. There's 7. So that allows me to say that at 7 and an output greater than 7, I'm sorry, an input greater than 7 is going to give me an output greater than 0. An input that's less than negative 2/3 is going to give me an output that is greater than 0. So when x is greater than 7, the output is greater than 0. And then when x is less than negative 2/3, my output is greater than 0 also. If for some reason they were looking for the other way, whereas at less than 0, then we would be looking at this range in between. Okay. Practice question from DP's style questions. We looked at one of these a while back. I've seen lots of these show up, or similar types of questions show up. So it says f of x equals 3 times some number x squared minus some number k plus 3 plus some number k plus 2. And it wants to know what values of k would output no real roots. So remember, how do we tell if something has real, imaginary, or 0, like a double root? We use the discriminant. So this term right here represents my a. This term right here represents, oops, we're going to have to put the x in there. Apparently I left that off when I did the scan and sent it to you. Represents the b, and this term right here represents the c. So we would do the same thing and say the discriminant, if the discriminant, no real roots, is less than 0, no real roots. So let's figure out what the expression for the discriminant would be. The discriminant is the part that lives under the radical on the quadratic formula. So there's b squared minus 4ac. We don't need the square root, we just need this part. So b squared would be negative k, I'm going to distribute that negative, minus 3 squared minus 4 times a, which is 3k, times c, which is k plus 2. I'm not going to go any further than that. I want you to do this one because this is the kind of question that might show up on your assessment later this week.